We continue the explanation of formation of complexes. As a summary, the complex is formed between metallic ion and ligand M plus L that give Ml. If the reaction is favored in direction 1, so this reaction is favored in the direction of formation of complex, that means this complex is stable. And if the reaction is favored in the backward direction, so Ml to M plus L, that means this complex is unstable. The condition of stability or non-stability of the complex can be determined by Kd or Kf. Suppose you have two complexes of same stoichiometry. The greater the Kf, the more stable complex. So the strengths of stability of a complex increase with the value of Kf or decrease with the increasing of the value of Kd. And any complex has a value of Kf and Kd. Kf and Kd of the same complex are related. Kf equal 1 over Kd. Another factor that affects the stability of a complex is the nature of the ligand L. In general, when L is polydentate, so it can do a bond or bonds with the metallic M by several sides. Therefore, the bond between the metal and the ligand is more stable, so we can say that the complex is more stable. So also, the nature of the ligand affects the stability of the complex. As the ligand is polydentate, it will stabilize the complex formed. So this is the second observation about the stability. We have a notation about the coordination number. Suppose you have a complex between FeC plus and SCN minus. FeC plus SCN minus give FeSCN 2 plus. How did I know the nature of the complex formed? Or how did I know the stoichiometry of the complex formed? In the data, they gave the complexes formed with their Kd or Kf. And in the data, I find that we have a complex FeSCN 2 plus. So this is the complex form when FeC plus is added to SCN minus. So what is the coordination number? Suppose in this figure, you have a complex given CuNH3 4 2 plus. That means around Cu we have 4 ligands. So the coordination number is the number of bonds between the metal and the ligand. The coordination number is equal to 4. In CuNH3 is 3 2 plus, the coordination number is equal to 3. We have 3 ligands around Cu. In CuNH3 2 2 plus, the coordination number is 2. And in CuNH3, the coordination number is 1. For some metallic ions, we add a ligand L, we obtain one type of the complex. And for other ions, if you add a ligand, you obtain several complexes. This is also the case of Cu2 plus. Suppose I have a beaker containing CO2 plus and another beaker containing ammonia and H3. CO2 plus is in the not very diluted, in the concentrated form or not very diluted form. CO2 plus is blue, and NH3 is colorless. So when I add NH3 to CO2 plus, it's given in the data that I have 4 types of complexes. These complexes are given. We could not predict in the first year the nature of the complex formed. The complex should be given. So in the data given 4 types of complexes. How did these complexes form? CO2 plus react with ammonia to give Cu and H3 2 plus. How did I know that charge? NH3 is neutral. CO2 plus has 2 plus charge. So when we do the bond between Cu and NH3, we should obtain the total charge of the complex 2 plus. Or the student can say that the charges in the reactant should be equal to the charges of the product. So in the reactants we have 2 plus, in the product we should have 2 plus. This is the first type of complex or the first complexation. Then Cu and H3 2 plus can add another ammonia to give Cu and H3 2 plus. Cu and H3 2 plus plus NH3 give Cu and H3 3 2 plus, and at the end Cu and H3 3 2 plus plus NH3 give Cu and H3 4 2 plus. How did I know this sequence? In the data given 4 complexes. So what is the meanings of 4 possible complex? When you add NH3 to Cu2 plus, you can obtain complex 1, complex 2, complex 3, or complex 4. And is given Kf1, Kf2, Kf3, Kf4. Pay attention that Kf1 is the formation of complex 1 from its initial metallic ion and its initial ligand. Kf2 is the formation of the complex 2 from the complex 1. Kf3 is the formation of complex 3 from complex 2. And Kf4 is the formation of complex 4 from complex 3. The stoichiometry of these 4 reactions is the same. 1, 1, 1. And in the other complexation reaction, we have practically the same stoichiometry. So, to compare the sequence of this complexation, of these complexations, I can compare K of reaction 1, K of reaction 2, K of reaction 3, and K of reaction 4. K1 is equal to Kf1, and pay attention that Kf1 is equal to the complex Cu and H3 2 plus concentration divided by the concentration of Cu2 plus at equilibrium times the concentration of NH3. Kf2, K2 equal Kf2, and Kf2 is equal to the concentration of the complex formed, which is Cu and H3 2 plus divided by the complex 1 Cu and H3 2 plus times NH3 at equilibrium. The student now asks that Cu and H3 is ion, so I use the concentration. Cu2 plus is ion, I use the concentration, and NH3 is liquid. In this case, NH3 is not liquid. NH3 is NH3 soluble in the solution. So this is NH3 aqueous. So it should be counted in the expression of K. And K3 and K4. If you compare K1 to K2, K1 is not equal or not greater 100 times than K2. 10 to the power 4, 0.2, and is not greater or equal than 100 K2. What is the meaning? So these two complexations occurs at the same time, but not with the same advancement. The first is more advanced since K1 is greater than K2. The first is more advanced than the second, but the first and the second occurs at the same time. This is also the case when we compare K2 and K3, and when we compare K3 and K4. So as a conclusion, when we add ammonia to Cu2 plus, we have formation of 4 possible complexes, and according to the value of Kf1, we have always Kf1 greater than Kf2, greater than Kf3, greater than Kf4. So the formation of the first complex is the easiest. This is the same analogy with the acid base. In the acid base, the first dissociation has Ka1, the second dissociation has Ka2. Ka1 is always greater than Ka2, so the first acidity is the strongest. If Ka1 is greater 100 times Ka2, so reaction 1 starts, and then reaction 2 starts. If Ka1 is not 100 times greater Ka2, so K reaction 1, or the first dissociation of H2A, or the first acidity of H2A, and the second acidity of H2A occurs at the same time, but with different advancement. So, as a conclusion, sometimes you add a ligand to a metallic ion, you obtain one form of complex, and in other examples, you add M to ligands, you obtain several complexes. These complexes are called successive complexes. 1, 2, 3, 4, and the nature of this complex should be given. I cannot predict. And to note that the first complexation is the easiest, and according to the value of Kf1, Kf2, Kf3, Kf4, I can know the sequence of formation of these complexes. We can write the formation of complex from its simple metallic ion and ligand, or we write the formation of the second complex from the first complex. When we write the formation of the second complex from the first, this K of reaction is equal to Kf2. Add reaction 1 and reaction 2. If you add these two reactions, if we add these two reactions, the first question, can I add these two reactions? Yes. I can work on the global reaction since these two reactions occurs at the same time. So we simplify by Cu and H3, we obtain Cu2 plus 2NH3 that gives Cu and H3 2 plus, and this K is K global. This K is equal to Kf2. Okay. So what is the difference if we write this reaction according to this form? Here we write the formation of the second complex from the first, and K of the reaction is equal to the constant of formation of the second complex. In this reaction, Cu2 plus 2 and H3 gives Cu and H3 2 plus. This is the formation of the second complex, not from the first. This is the formation of the second complex from its initial metallic ion and its initial ligand. So K for this reaction could not be written Kf2, is written K global, or by convention is noted K global 2 is noted beta 2. This is beta 1, the formation of the complex from its simple ion and ligand. Beta 2 is the global reaction of formation of the second complex from its metallic ion and its ligand. Beta 3 is the global K of the reaction of formation of complex 3 from its simple ion and its simple ligand. And beta 4 is the global formation of complex 4 from the initial metallic ion and the initial ligand. So now you have to pay attention. In some exercises, they wrote in the data Cu and H3 2 plus. Some exercises they gave Kf2. Other exercise they gave beta 2. If Kf2 is given, that means you can write the formation of this complex 2 from complex 1. And if beta 2 is given, you can write the formation of this complex 2 from its simple metallic ion Cu2 plus and its simple ligand NH3. And pay attention, beta 2 is different from Kf2. So what is the relation between beta and K? In this form, beta 1 is equal Kf1, since this is the formation of the first complex. In the second reaction, beta 2 is equal to Kf1 times Kf2. Multiply Kf1 by Kf2. So you simplify Cu and H3 with Cu and H3, you obtain Cu and H3 2 plus divided by Cu 2 plus times NH3 squared. So this is the formation of the second complex from its ion Cu2 plus and its initial ligand NH3. So this is the beta 2. So beta 2 is equal Kf1 times Kf2. Beta 3 is equal Kf1, Kf2 times Kf3. Beta 4 is equal Kf1, Kf2, Kf3 times Kf4. So as a relation, beta is the multiplication of Kfi when I is between 1 and n. As a conclusion, in the case of the successive complexes, in the data given, we can have Kf or beta. And do not forget that beta is identical to K global. For complex 1, beta 1 is equal Kf1. For complex 2, we have Kf2 and we have beta 2, and Kf2 and beta 2 are related. Beta 2 equal Kf1 times Kf2. For complex 3, we have Kf3 given or beta 3 given, or global reaction of 3, and beta 3 equal Kf1 times Kf2 times Kf3, and this is also the same for Kf4 and beta 4. So in the exercise, we should work on Kf or we work on K on beta. It depends on the data given. So we have to look first in the complexation, we have to look to the data given. Predominance domain of species. The reaction of complexation, M plus L, that give ML. So this is Kf of the reaction. And Kf of the reaction is equal to the concentration of Ml divided by the concentration of M times concentration of L at equilibrium. So I will do log Kf equal log Ml divided by M times L. So log Kf equal log Ml divided by M times L, and pay attention that these concentrations are at equilibrium. So log Kf equal log Ml minus log M minus log L. I will pass to minus log L equal log Kf minus log L equal log Kf minus log Ml, and minus log M become plus log M. And we know that Kf equal Kd. So log Kf equal 1 over Kd implies log Kf equal minus log Kd. So what would be the relation? Minus log L equal log Kf minus log Kd minus or plus log M minus log Ml minus log L. So this is PL minus log Kd, this is PKd, plus log M divided by L. So look to this relation. This relation is identical to the Henderson equation. Henderson is pH equal pKa plus log base divided by the acid. So plus log base is the acceptor divided by the acid, which is donor. So the P of the particle exchanged is equal to P of the characteristic of acid base plus log acceptor and donor. If I suppose that the particle exchanged between M and Ml is L, if you suppose that L is the particle exchanged, you write PL equal P characteristic of the complexation I prove that this is PKD minus, instead of log F, we put minus log KD, so PKD plus log. L is the particle exchanged, so L is given to M, so M is acceptor. So plus log acceptor M divided by the donor, which is ML. This is the same analogy of Henderson equation. P particle exchanged equal PKD plus log acceptor divided by donor. If I suppose that the L is the particle exchanged, so the acceptor is M and the donor is ML. If I suppose that M is the particle exchange, so it becomes PM equal PKD plus log. L is acceptor of M plus log L divided by ML. As a conclusion, in the acid base, we have one particle exchanged, which is the proton, and we proved the Henderson equation from Ka, which is the characteristic of the acid-base couple, and we proved that pH, P of the particle exchanged, pH equal P K characteristic, which is Ka, plus log acceptor divided by the donor, so plus log base over acid. If you forget the formula or the similar formula in the complexation, you apply Henderson for the complexes. You can say P particle exchange, I suppose that this is PL, equal PK characteristic, that is PKD, plus log acceptor. If I start with PL, that means M is acceptor of L, so plus log M divided by ML. Or if you suppose that the particle exchange is M, you can write PM, and L is acceptor now of M, so PM equal PKD plus log L divided by ML. In the acid base, we have one formula, pH equal PKD, pKa plus log base over acid. In the complexation, we have two formulas, one on PL and another on PM. PL equal PKD plus log M divided by ML, or PM equal PKD plus log L divided by ML. Which of these two formulas will be used? It depends on the request in the exercise. It depends on the questions of the exercise. Sometimes he asked to work or to calculate PL. In other examples, he asked to calculate PM. So this is the analogy between acid base and complex. In the acid base, we talk about HA, A minus. In the complex, we talk about ML, L, or ML, M. The particle exchanged in the acid base, P equal H plus. In the complex, P particle equal M in this case, or the particle is equal to L in the second case. In the acid base, with the characteristic is Ka. In the complex, the characteristic is Kd and not Kf. In the acid base, we ask to calculate pH. In the complex, we ask to calculate PL or PM. It depends on the exercise. The acid is the donor. The ML is the donor. ML is donor of M, or ML is donor of L. The base is the acceptor. The acceptor is M, acceptor of L, or L is acceptor of M. The Henderson formula, we have one Henderson formula, pH equal pKa plus log base over acid. In the complex, we have two formulas, PL equal PKD plus log M divided by ML, or PM equal PKD plus log L divided by ML. So the domain of predominance of complexes. I will explain this in the third part.